Hello everyone, I'm Zhen Li from RealC. I will present our work, Multi-View Inverse Rendering for Large-Scale Real-World Indoor Scenes. Our goal is reconstructing 3D assets, including global illumination and materials from sparse posed HDR images. To this end, the first challenging is how to represent global lighting efficiently. The differentiable path tracing is able to model such light transport, and the image-based lighting could directly represent the global lighting at a location. However, above representations are computationally expensive or incompact. Therefore, we present a compact hybrid lighting representation to model global light transport efficiently. We first reconstruct the geometry and HDR texture with existing 3D reconstruction algorithms. Then, the incoming lighting of X in the rendering equation could be calculated with the outgoing lighting of Xi, and the HDR texture is approximated as the outgoing lighting. Such approximation is reasonable in most common cases since the diffuse lighting often dominates the scene. Finally, we pre-compute the irradiance based on the TBL to decrease rendering noise and accelerate the following material optimization. The second challenging is how to disentangle the ambiguity between materials from sparse view images. The learning prior successfully provides a nice constraint for the object-centric scene, but fail in generalization to large scenes. The local smooth term and bilateral smooth term only constrain smoothness, but the actual value is not constrained. In our method, we introduce a segmentation-based 3-stage material optimization strategy to explicitly recover the physically reasonable materials. Specifically, in the stage 1, we only optimize the albedo with diffuse photometric loss and semantics-based albedo smooth loss. In the stage 2, we first render images based on input poses with low roughness to find virtual highlight regions for each semantic class. Therefore, we can optimize physically reasonable roughness in these regions. Then, we propagate such reasonable roughness into the region with same semantic segmentation. In the stage 3, we fine-tune all material textures and only roughness are optimized based on the priors of semantic segmentation and room segmentation, which makes the roughness of different rooms smoother in a soft manner. Let us look at the qualitative results compared to previous methods on real dataset. Our method reconstructs globally consistent and physically reasonable SVBRDFs, while other approaches struggle to produce inconsistent results and reduce ambiguity between materials. The results on synthetic dataset also show that the proposed method outperforms the state-of-the-art. Finally, we demonstrate results on several applications. For material editing, when we only edit the estimated albedo, the realistic specular reflectance and shadow are also existing. When we only edit the roughness, the specular highlights are changed and diffuse reflectance remains the same. For relighting, when we change the color of the light sources and move its position, the specular reflectance on the floor are physically reasonable. For editable novel view synthesis, we re-render novel views based on edited material assets. The rendering images exhibit physically reasonable appearance when we edit the material. Note that the view-dependent specular highlights reasonably change as view changes. Thank you for watching.